So this is the second lecture in the series. We did have tutorial yesterday, and yes, at some point today we should decide whether we should hold a tutorial today or wait till tomorrow. But in any case, my lecture slides will be posted online together with a complete set of tutorial problems, like of all levels, like sort of beginners, sort of experts, medium, and open problems. One thanks to me, one thanks to Luke Hoffman. So please take a look at them and enjoy and ask questions. So where were we yesterday? Okay, what did we do? So we want to classify knots. I mean, it's a worthy goal. And one way to do it is to construct knot invariants. And as we've seen, there's a problem with knot invariants. They're either not computable or imperfect, meaning they're not complete invariants. They cannot distinguish all knots and links, or sometimes both. And that means that we do need stronger invariants, better invariants that can distinguish more knots and links. And then the question is like, well, how do we get them? And one way is to sort of upgrade. To do that is to upgrade invariants that you do have. Okay, so find a way to improve them. Khovanov homology is such an example. So Khovanov homology is a lift of the Jones polynomial or a categorification of the Jones polynomial. Again, the term categorification is not a well-defined term. It can mean many different things, but you know, the idea is there in the spirit. In this particular case, what that means is that the Jones polynomial can be recovered as the Euler characteristic of Khovanov homology. So what does that mean? Khovanov homology is a bigraded theory. So we're going to sum over all J, which means that we're summing over rows. And then we take the alternating sums of ranks of Khovanov homology. Again, if we're working over a field, then we have just dimensions of vector spaces. And that's called the Euler characteristic of Khovanov homology. Well, that's just the Jones polynomial. And again, the Skene relation for the Jones polynomial is lifted or categorified by the short exact sequence of Khovanov chain groups, which in turn gives us the long exact sequence in Khovanov homology. Okay, one thing that I want to point out again from as a summary from yesterday's lecture is that I'm sure you all remember the sort of cube construction. And we sort of had an example in which we replace every polynomial contribution from a Kaufman state with a certain space that I've called A, and certain tensor product of these copies of A. And what I hope came through in the previous question, in the previous lecture, is that this choice of algebra A, which is z of x quotient by x squared, actually makes sense. So what do I mean by makes sense? Well, number one, its graded dimension is equal to the Jones polynomial of the unknot. So somehow that's good, right? Because we assign the algebra A to the unknot and it decategorifies to the Jones polynomial of the unknot. But then something that sort of gives us a hope that we're going to get a better invariant, in particular that we're going to get an invariant that can associate something to knot cobordism, is the fact that this particular algebra has a Frobenius algebra structure, and that's an algebraic part of the sort of topological picture of knot cobordisms. So it's the algebra structure that sort of like faithfully represents something that we sort of feel is very natural deformations of cobordisms in topology. Okay, and then these are my examples that Khovanov homology is stronger than the Jones polynomial. This is Khovanov homology of a knot 5-1. This is Khovanov homology of a knot 10 sub 132. And in which ways can Khovanov homology be stronger than the Jones polynomial? So remember, if they have the same Jones polynomial, that means that the Euler characteristic of this table is the same as the Euler characteristic of this table. Okay, so it can be stronger in two ways. Either you have z here, and again, in the corresponding degree, you have z here, but then somewhere in this row, it doesn't have to be here, somewhere in this row there's some torsion, z2, z3 or something, that's just going to be invisible to the Euler characteristic. Euler characteristic only takes into account the free part of Khovanov homology. That's number one. And a second way in which it can differ is that in this degree -1 that I did not write here because it's trivial, you can have a copy of z, and a copy of z in any field that's one off, sorry, that's odd number of times off. So it may be, if you have this z here, that it may be in -1 or -3 or -5, it doesn't matter, because ranks of these two z that are 1 will appear as +1, -1 in the Jones polynomial, in the coefficient of the Jones polynomial, so they will just cancel out. So if you have something like this, that just means that the coefficient of the Jones polynomial in this particular grading -1 will be 0. So you sort of cannot distinguish the fact that there was nothing in Khovanov homology there, or there were two groups with the same free part, but in sort of gradings that come with opposite signs. Okay? Does this make sense? Okay. So one thing that I sort of like want to point out now is that Khovanov homology is a homology theory, right? So theoretically, we should be able to do everything that we can do with standard singular or simplicial homology. And in particular, what that means is that we can compute it with different coefficients. Okay, so if you're not familiar with this, that just means that when we're computing over z, that means that we are taking formal combinations of chains and over z. So, you know, we can have 3 of this plus 5 of this and so on and so on. If you're working with z2 coefficients, that means that if we have 5 of something, that's the same as having just 1 of that. Or if you have 4 of something, that's like it's not there. So working over z2 means the coefficient can be either 0 or 1. Okay, so basically we can compute Khovanov homology in general with zp coefficients for, let's say, any prime p, or z2 in particular. That's a very useful one. And here's like a little bit of standard algebraic topology. There's a UCT, or universal coefficient theorem, that sort of tells you how are these homology related. Okay, and basically what it says is that if you want to compute any homology, well, I wrote cohomology here, but okay, don't worry, it's the same here. So with ZP coefficients, that's the same as computing the homology over Z and tensoring with ZP, plus adding the so-called Tor part of the n plus first homology theory over ZP. Okay, in the language of Khovanov link homology, and again, I wrote it as a cohomology, which it actually really is, but don't worry about it. That just means that you take the homology over Z, tensor with ZP, or add this Tor part. If you don't know what the Tor part is or how to tensor things, don't worry. Well, here's a little intro on how to compute them. And basically, it's as simple as taking the greatest common divisor of you know, ZP tensor ZQ. Well, just that's Z GCD of P and Q. So for example, Z2 tensor Z3 is 0 because they have no common divisors, and Z6 tensor Z4 is Z2. Okay, so all I want to sort of say is that it's not hard to compute these things. You may wonder, well, why do you want to compute it? Because it looks from the right-hand side, it's anyway determined by the integral Khovanov homology. Khovanov homology computed over Z. Well, that's true, it is. So any homology computed over some ZP coefficients is determined by the integral homology, which is great if you know how to compute the integral homology. But computing integral homology is hard. So sometimes you may actually be able to compute Khovanov homology with certain ZP coefficients, or any homology over ZP, and then sort of try to extract information, what happens over Z. So somehow over Z is the strongest theory that you can have, but it's usually hard to compute. Okay. There are many different versions of Khovanov homology, and there's actually many different constructions of Khovanov homology that are either equivalent or conjecturally equivalent. But I'm going to talk about those versions on Friday. So now I just want to introduce you to the existence of certain kinds of Khovanov homology. So somehow, once the Khovanov odd homology was invented by Oswald Rasmussen and Sabo in 2007, people started calling the Khovanov homology even Khovanov homology. So if you encounter that in any papers, it's just the standard Khovanov homology. So I'll drop the subscript here, but usually it's sort of KH sub E. And then in 2010, Krzysztof Putyra actually came up with a unified theory. That's a more complicated algebraic construction. That's a theory that works over a different ring. So remember, we had z of x quotient by x squared, which means that x squared is sent to 0. And here he's working over the ring z, well, some variable, doesn't really matter which one, xc squared minus 1, which of course factors into xc minus 1, xc plus 1. So actually, if you want to relate those, let me sort of just jump here. You can actually see that if you sort of compute the unified chain complex over xc minus 1, you sort of get the standard even chain complex, Khovanov chain complex, and otherwise you get odd. So unified theory actually contains both standard Khovanov homology and odd homology. I will not give you the construction of Khovanov odd homology. It's beautiful. It's the same essentially as the construction of Khovanov homology, except that you have some extra data, which makes your life a little bit harder, and there's like many technical choices that have to be made. But you know, those subtle differences will give us something more, and I'll say something about relations. But there's beautiful lectures that were recorded at CIRM by Paul Turner from, I think, less than 2 years ago. And in his first lecture, instead of giving the construction of Khovanov homology, he constructs the Khovanov odd homology. It's just on YouTube. I will encourage you to take a look at it. It's very good, and it's very conceptual. So, and then again, you can compute either one of these theories over Z2 coefficients, and that's what I'll call mod 2 Khovanov homology. So how are they related? Okay, well, Khovanov homology over Z2 is actually the same as the odd homology over Z2. They're not the same when computed over integers. And then you can sort of see that if, again, because that's my running examples, like we sort of saw how Khovanov homology of the knot and its mirror are related. That was kind of the last example I did yesterday. So both Khovanov chain complexes and homologies are dual for the standard homology. However, in the odd Khovanov homology, we sort of lose the duality on the level of chain complexes. So somehow this construction sort of messes things up. But again, on the level of homology, everything works out. Now, you would say, well, why do we even bother computing Khovanov or Khovanov odd homology now that we have this unified theory? Well, because it's even harder to compute the unified theory than it is to do this, and it's actually, you know, really algebraically intensive, because that means that you need to know how to, you know, we all know how to classify modules over Z, right? That's not hard. But here you actually have to classify modules over this ring. That, you know, I'm sure it's doable, but we are topologists. So anyways, one beautiful recent result that, again, I'm not going to go over in details. It's a work of Alexander Shumakovich and Chris Putyra and some other people. And basically, I do want to apologize officially, I guess, in front of cameras. I should probably look straight into the camera. This field has basically exploded since I became a grad student. And I'm sure that I'll miss giving credit to some of the people. So I apologize in advance for that. But anyways, so this is a very, very beautiful idea. Again, because although you cannot compute this Khovanov unified theory, there's a way to extract a new type of invariant that takes a form of a rank of the image of a certain map. Okay? So it's somehow very subtle. It's known in algebraic topology that there can be sort of various operations of homology and sort of higher structures like Steenrod square or Macy products or something like that. But here what they actually do, they sort of notice that, again, if you don't understand some of these words, sort of don't worry about it, but that you can have an action of the unified theory on the standard Khovanov homology and odd Khovanov homology. And what that means is that somehow you can compute some operations on these homology theories. And once you have some map, you can definitely compute a rank, okay, of that map. And it turns out that that's a knot invariant. Okay? Great. I mean, it takes time to prove that. But it also turns out that it's trivial for alternating knots. Okay? So it won't tell us anything about alternating knots, but it actually does things for non-alternating knots. So instead of going into any of the details, again, I'm going to tell you about computations done by Alex Shumakovich, where out of all 201,702 knots, we did most 15 crossings, and I hope Marielle will forgive Alex that mirror knots are not included. There are 99 pairs that cannot be distinguished either by Khovanov or odd Khovanov homology. They're the same. However, these homological operation invariants do distinguish them. Okay? And then I'm going to scale down, and among, you can see the jump between 14 and 15 crossings. That's why this is in the slide. Among 33,672 knots up to mirror images, with at most 14 crossings, there are 9 pairs with the same property, right? So we go from 9 to 99, okay, that cannot be distinguished. And again, homological invariants do distinguish these 9 pairs. However, they don't distinguish the mirror images of these pairs. Okay, and I hope I'll be able to somewhat illustrate that. Yes? I think so. I'm not sure, but yes. It's not a sequence of operations. There's just like a few different operations. Yeah, and then you just compute their ranks. There's, let's say there's like 4 of them that are like particularly strong, and then you just compute their ranks, and you get like 4 different numbers, and they can distinguish them. Anyways, but let me sort of just point out, this is again a non-trivial result that the unified theory is actually stronger invariant than both of Khovanov and odd Khovanov combined. Okay? Other questions? So this is a very recent result. Okay, so here's a version of Khovanov homology that I will tell you about, actually, because it's very simple, but yet, it gives you some different results. So you can take reduced Khovanov, reduced odd Khovanov, and the construction is the same. However you construct these homology theories, you sort of pick a base point on your knot diagram. And then when you do your cube of resolutions, you say, if that particular circle has the base point on it, that circle can only be labeled by X. Cannot be labeled by 1. Usually it's combinations of 1s and X's and so on and so on, but this one can only be labeled by X. That's what I mean by reduced. Well, that's I guess what they mean by reduced. And of course then you need to prove that this reduced Khovanov homology does not depend on the choice you made, and that can be done. So you do get a link invariant that's independent of the choice of base point. However, that's only true if you have a knot. If you have a link, this invariant will be different depending on which component of a link you choose. But I mean, that's sort of trivial to see, because just think of a split link. Here's a trefoil and here's a figure 8. And if you pick a base point on a figure 8, and you can label that one only with X, like it's going to be different than if you pick a base point on a trefoil. So again, maybe this theory works better for knots than links. But then, here's a result by Alex Shumakovich from 2004, which sort of says, well, Khovanov homology, standard one, computing over Z2, is actually easily obtainable from reduced Khovanov homology. You just tensor it with something. Okay, so some of the loss of information is not too big. And then there's a similar result with the odd Khovanov homology, which actually just says that you get 2 copies of the reduced one shifted a little bit. So again, I did not go over details. Again, what I'm trying to do here is just sort of paint overall picture about how these different versions of Khovanov homology relate and what can they give you. So back to the computations of Khovanov homology. This is Khovanov homology of this 16 crossing non-alternating knot. And, you know, I guess there's many different software packages to compute Khovanov homology, including the one written by Dror Bar-Natan, his students and collaborators, the one written by Alex Shumakovic, and then there's the one by Cottonseed. Again, let me just sort of emphasize that these algorithms have exponential complexity in terms of number of crossings, so it's hard to compute it. There's some shortcuts, but again. So what do we see here? Again, this one here stands for Z, this 2 stands for 2 copies of Z, Z plus Z. And any number that has subscript means that there's that many copies of torsion. So for example, 10 sub 2 means that there's 10 copies of Z2. Okay? And then what's curious here is that, for example, look, there's Z4 torsion. In general, in standard Khovanov homology, there's a lot of Z2 torsion. There's some Z4 torsion, or again, even torsion, and somehow torsion of odd order is hard to find and hard to understand. And we'll be talking about it tomorrow in like full detail. So, but what happens when we take the mirror of this knot? And again, I'm computing things over Z. Okay, so let me just show you in pictures. Remember, what I've proved is that there's a duality. They're isomorphic, but the indices change. So ijth Khovanov group of a link is isomorphic with minus I minus j Khovanov group of the mirror, the free part. Okay, well that means that, you know, whatever was happening, whatever was happening here, like 1, 4, 7, well that's going to be happening kind of here, 1, 4, 7. But what happens with torsion is the torsion will switch places. So what I've emphasized here is that this 1, 4 actually moves to, well, of course, this side, but it also shifts up or down. So that's the result of this universal coefficient theorem that somehow says that nth torsion here comes from nth Khovanov homology, plus you can have some terms from n plus first homology. So there's like a shift there. So I'll put them side by side, but then they're going to be, okay, sorry, here, but then they're going to be less visible. Okay, I've just put those two big diagrams side by side, and here I've emphasized the torsion that somehow lies along this line here. This line is called the diagonal. And when you look at the mirror of this knot, then it sort of like moves kind of up, sort of it flips to the other side. Okay, well, let me tell you what the effect it's going to have on something that's called homological thickness or homological width of Khovanov homology. So this is basically just like one of the patterns that appears in Khovanov homology. You know, as you can see, Khovanov homology is a bigraded theory, so you can just represent it on the integer lattice, right, 2-dimensional one. Here are some computations. So homological width of a knot is actually the homological width of Khovanov homology. It's the number of consecutive diagonals of slope 1, 2 that are sort of that have non-trivial entries. So here you can see that all of the non-trivial of Khovanov groups just lie on 2 consecutive diagonals. That means that the width of this particular knot is 2. There's only 2 diagonals. Okay. However, here you sort of see that you need 3 consecutive diagonals. So here homological width is 3. By the way, I was hoping, but it's early in the morning now, so I'll just tell you that someone will ask me why we have only, you know, every other number in these tables. It's actually not hard to prove that that's always going to be true. You're always going to have something, nothing, something, nothing, and you should sort of prove that. So if you have, it just depends on the number of components. So in the gradings that have the same parity as the number of components, you're going to have non-trivial entries, and then in the other ones, you're going to have just zeros. So somehow the slope is always 1, 2 here. Okay, but so this is something that you can just like get from looking at the experimental results, right? You're sort of looking for patterns. You kind of think of computation of Khovanov homology as your data, and you see, well, what can I say about it? And I'm going to tell you a little bit more about different patterns than appear in Khovanov homology. This is one of them. So the effect that I've tried to explain a moment ago between the 16 crossing knot and its mirror image is that what's going to happen here is that the actual knot will require 3 diagonals. So it's going to be homological with 3, which means it's thick. If it's homological with 2, then it's called thin. So you can see that there's this diagonal, the top one, and this one goes through the middle, but those sort of these red entries require yet the 3rd diagonal. They're sort of like off. However, when you take the mirror image, because of the universal coefficient theorem, things get shifted, and now these entries that belong to this torsion, they will actually become a part of either this lower diagonal or the upper diagonal. So the mirror image is actually going to be thin. Okay? And just to make sort of things, you know, more interesting, you can sort of compute this homological width or thickness over different rings, right? Because now we know how to compute over Q, which is just a vector space thing, over Z, which is the integral Khovanov homology, over Z2, and so on and so on. And what you can actually see here, well, this one is definitely thick. It needs 3 diagonals over Z. It ends up being thick over Z2, but Khovanov homology of its mirror image is going to be thin over Z, as we see here, only 2 diagonals, but it's actually going to end up being thick over Z2. So the question, does thickness change with respect to the ring that we're computing over? The answer is sometimes. We cannot really tell, but somehow almost all combinations that you can imagine can happen. So sometimes the homological width over Q is strictly smaller than integral homological width or homological width mod 2, but sometimes these two are not equal. So homological width over Z is smaller than the homological width over Z2. And then you sort of see, well, which knot properties sort of like tell us whether the knot is going to be thin or not, or just in general, this homological width is just a number, so can we sort of see what kind of properties it has? And this is sort of like a common one, so it actually behaves nicely under the connect sum. So anyways, an operation of a connect sum means just that you, did someone mention it? Yes, maybe someone mentioned it already. So you take one knot, and then let's say you take the other one, and you break it, let's say in 2 places, and you reconnect. That's a connect sum of 3-1 and 4-1. And it turns out that the homological width, let's say over Q, behaves nicely. So it's sort of additive. You just need to subtract 2. And in particular, what that gives us is that the connect sum of 2 knots is going to be thin, in particular thin over Q, if and only if both constituent knots were thin. Okay, so that's something that you can sort of say. And then there's an invariant that I won't tell you much about, but it's very sort of topological in its nature, and it's basically defined based on the surfaces that sort of span your knot and have your knot, well, whatever, all homological, sorry, the 2 homogeneous smoothings, all positive and all negative in its boundary. So this derived genus, which I denote here by GT, actually gives an upper bound on the homological width of Khovanov homology. So homological width of Khovanov homology minus 2 is strictly, it's less than or equal than the derived genus here. And this is a result by Chepenerka, Kaufman, and Stolfutz, and independently by Manturov. And maybe Manturov actually got it sooner. So basically, but we don't know, given the knot, can we determine whether its Khovanov homology is thin or thick? That would be like a question that's like worth answering, and I hope it's going to become clear by the end of this lecture why is that an interesting question. Okay, and you think about the Jones polynomial. Okay, so here's, I think, 2 background slides. So in case you don't know what the signature of a knot is, this is going to be like a very, very, very crash course into what the signature of a knot is. It is a knot invariant. It is a number. And it can be, but it's computed from a certain cipher surface, a certain surface that has a knot in its boundary. Okay? And here's my example. So you sort of pick a surface. such that a knot, which is here represented in yellow, lies in its boundary, and I won't tell you how to construct it. And then you take that surface and you construct something that's called a ciphered form of that surface, and that's basically a pairing on the first homology of that ciphered surface, and that's just a regular algebraic topology that sort of takes a generator, a class in H1, pairs it with another class in H1, and just spits out a number. And the way that that number is computed is that if your classes are called A and B, then you compute the linking number of a positive push-off on A and a negative push-off of B. And you know, you need to know the normal boundary and so on and so on. And then what you do, you sort of pick a basis for your first homology, and then you take a matrix that's representing this pairing. Okay, that's matrix V, and then you just compute a signature of a matrix V plus V transpose. And the signature of that matrix is a signature of a knot. And you know, then you need to figure out what that's meaningful. It is a knot invariant. It doesn't depend on any of the choices of the basis or anything else, or ciphered surface. And in particular, the signature of a knot can be computed from some data on a knot diagram, and the signature of a different matrix that's actually very combinatorial. It's called the Goritz matrix. That again, I won't define for you, but there's like a very beautiful formula about Gordon and Litherland. And in particular, that Goritz matrix is a matrix. You can compute its determinant. And it turns out that even the determinant of that matrix is a knot invariant. So what I'll define is that the determinant of a knot, it's actually just the absolute value of the determinant of that matrix. Okay, so why am I telling you this? I'm telling you this because, well, signature of a knot will appear in a second, but determinants actually used to construct a very natural, and in particular very natural from the point of view of Khovanov homology, generalization of a class of alternating knots. There's many generalizations of alternating knots. Somehow they're easy to work with. And this is one of them. So quasi-alternating knots consist of the smallest set of links, such that a knot is one of them, and all of the links L that have this kind of recursive property. So you basically say that you can find a diagram of L and some crossing in that diagram, such that if you resolve in either one of the ways, if you do either zero smoothing on, this is what I call infinity smoothing at that crossing, the two knots that you get are still quasi-alternating. And the determinant of the knot we started with is the sum of determinants of these two knots that we have obtained. So again, I won't prove this, but alternating knots are a subclass of quasi-alternating knots. Okay? And here's the theorem proved by Yuson Lee in 2002 that basically said that every split non-split alternating link is thin. And it's thin over any ring that you want to work with. So what it means is that Khovanov homology over any ring of non-split alternating knot lies only on two diagonals. Okay? So instead of giving you this proof, for I guess pedagogical reasons, I'm going to give you a later proof that's by Manolescu and Osvat that's a generalization of this one. So what they proved in 2007 is that actually quasi-alternating links are thin. So you sort of have a stronger result than the previous one. And in particular, you can do that by showing that the reduced Khovanov homology is trivial unless it lies on this diagonal, well, of slope 2, right, 2i minus j, such that their difference is actually equal to the signature of a knot. So what this is saying is that we know that Khovanov homology and alternating split links will lie on two diagonals, and then this actually tells us exactly where in the rectangle of that's representing Khovanov homology, where in the plane those two diagonals will be. Okay? So here's a rather technical, but I think maybe somewhat insightful proof that I'm, again, not going to present in full detail, but I hope the sketch will sort of be enlightening enough. So we have L0, L let's say this is a positive crossing L0 and L infinity, and there's like a technical lemma that sort of says that if determinant of L0 and determinant of L infinity are greater than 0, and then we have this quasi-alternating condition here, then for a certain constant E, that's just the number of negative crossings in, sorry, this should be D0 minus number of positive crossings in what I should call D infinity, then the differences between their signature is 1, and the differences between these other signature is this number E. Okay, well, why do we need this theorem? Well, the way that, sorry, this lemma. Well, the way that we're going to prove the theorem, we're actually going to invoke a version of the long exact sequence in Khovanov homology with sort of slightly different grading. So number one, notice that quasi-alternating knots satisfy exactly this condition. It's a quasi-alternating condition, so we can use this lemma. And if you look at the standard Khovanov long exact sequence in which we emphasize this grading delta 2I minus j, then the long exact sequence looks like this. You have some number, so this stands for some I, and this should be in a plus half the signature of L1, and then another grading that's just Khovanov of L, another one of L0. Again, this is here a connecting homomorphism. You can compute how these degrees here change based on this lemma. And you're going to see that they sort of change precisely by 1. Okay? But while the degrees are changing by 1, you're simplifying your knot, right? Because you're looking at both smoothings. So you can just continue doing that. Okay? So this exact sequence holds for L. Well, I can get 2 new exact sequences with different gradings, one for L0 and one for L1, and then again apply the same lemma, and again and again and again, and eventually I'm going to make it to the unknot, right? I've simplified, or an unlink. I've simplified things long, you know, fine enough, and basically it's going to, the process is going to end when you reach the unlink, and if you sort of look at it, the Khovanov homology, it's obvious the Khovanov homology of the unknot is thin, and so is the Khovanov homology of the unlink. And you just sort of like build your way up, because we know that if the two constituent knots are thin, right, this is this property, then, sorry, oh no, that's connect sum, sorry. Then we can sort of like, sorry, just use, sorry, forget about that. Then we can just use the inductive argument and sort of build our way up to say that L was thin too. Okay, by the way, if you're reading the original paper, they use a different convention that I've used here, different than Barnatan and so on and so on. So hence, this is a leftover minus here. It should have been just a signature and not half a signature. So here it's corrected to be consistent with our lecture notes, and they have a different convention in their paper. Okay, so why is this thinness result important? Well, let's just think about it. Everything, so how does Khovanov homology look like? Well, it's in this rectangle, and then we have certain diagonals, but now there's only 2 diagonals, and in particular, if we work with the version of Khovanov homology, we're going to get only 1 diagonal. And we compute the Euler characteristics, and none of the things that I told you about, if you look at the free parts, can happen. You cannot, there's no cancellations to happen. You cannot have z and z that are contribute +1 and -1 to the coefficient of the Jones polynomial. So if your version of Khovanov homology looks like this, then you basically know that the ranks of these groups are equal to the corresponding coefficients of the Jones polynomial. And then, based on the previous theorem, we know that this diagonal is where the signature of a knot is. So it's not here, but it's precisely where the signature is. So that's basically a sketch that the free part of Khovanov homology is completely determined by the Jones polynomial and the signature of a knot. Okay, so that's maybe disappointing result, but you know, maybe not. However, that's not true of knots that don't have thin Khovanov homology. So in particular, adequate non-alternating knots are known to be R-thick, meaning they lie on more than 2 diagonals. So what I did not do for you, I did not define what adequate knots are. adequate knot is one for which there exists a diagram, D, such that when you compute all 0 and all infinity smoothings, so they're homogeneous smoothing. We resolve all crossings in the same way, either this one or this one. You're going to get a collection of Kaufman circles. And if it so happens that there's no circle such that two arcs came from smoothing one crossing, then the knot is called adequate. Right? So if this never happens, if when you smooth a crossing, you always get arcs in different circles, then your knot is adequate. It happens in both of these cases. So again, it happens so that the adequate knots are also a strict generalization of alternating knots, but sort of like different than quasi-alternating. So that's definitely true. And here's another interesting result that's kind of easy to prove in the spirit of things that we were mentioning here. So the reduced Khovanov homology of a non-split alternating link actually has no torsion. I guess two torsion. That's my first sort of result about torsion. We're going to talk a lot about torsion here. So there's a universal coefficient theorem that gives us short exact sequences. And then again, I showed you two, both of which feature ijth Khovanov homology of your knot. So I want to show that there's no Z2 in the reduced Khovanov homology in ij grading. I'm going to do that by contradiction. So I'm going to assume that there is Z2 torsion in there. Okay? And then let's look at these highlighted versions. So if there is torsion, Z2 torsion here, then from this part, it will contribute a non-trivial term to the reduced Khovanov homology in ij grading. Okay? But if there is Z2 torsion there, then it's could contribute torsion. It's going to contribute some non-trivial element to KH of I minus 1j. So what I get is that there's two diagonals that are non-trivial. And that's a contradiction. It only leaves one diagonal. So there could not have been any torsion in Z2 torsion in KH of ij to start with. Okay, so this is like one of the ways how you can use sort of homological width to sort of prove other facts about Khovanov homology. And again, long exact sequences and short exact sequences are very important tools. So here's maybe my favorite pattern in homology. And again, it's hard to maybe see. I don't know if there's any chess players here. Yes, so there's pawn moves and there's knight moves in this Khovanov homology grid. So for example, let's see. There's the green 1-1, where sort of a copy of Z and a copy of Z are just lying on top of each other. So it looks like this. Okay, and that's the pawn move. And then there's a move that looks like this. Well, okay. And then sometimes that move, that ZZ, has a Z2 associated with it here. Just an element of a torsion. So, yeah, let me sort of show. So maybe this is a thin one. This is 818. And you can sort of see there's a 3 and a 3, and there's like 3 copies of Z2 here. And then, for example, here there's a Z and a Z and 1 copy of Z2 here. And then this is actually 3/4 torus knots, I think is 819. Again, in this zeroth grading, I have a pawn move, and then here, I think maybe they're more obvious sort of knight move pairs. And then again, sometimes they come with the torsion associated with it, sometimes they don't. So that was a experimental observation. It's still a conjecture, an open one, posed by many people, most of them who did computations. So I think Barnatan was the first to compute and observe many things. And then there's Staros, Garoufalidis, and of course Khovanov, who sort of conjectured that Khovanov homology, this whole grid, can be actually, it's very organized. It's sort of split into some of these night moves and the pole moves. And well, it's still open. It's proved for. That's an excellent question. I'm not aware of any explicit results, but I would not be surprised if there's some. I'm not sure. I'll tell just a little bit more about it, but yeah, I'll have to think about it. Yeah. So it's true for thin links, and I'll try to sketch the proof for you guys. So what does it mean for thin links? It's true for definitely non-split alternating links, but for any knot or link whose Khovanov homology lies on 2 diagonals only, this is true. There's only night move pairs and that one pawn move. It's true also for knots whose homology is computed on 3 diagonals, and there's no counterexample known. But we don't know how to prove it in general. Okay, and here's how you attempt to prove it for thin knots. So it's a result by Yuson Lee from 2002, and it's really, really clever. So you can pick which coefficients that you want to work with. Let's sort of stick with Q. And what she did, she actually defined a new map on Khovanov homology. So sort of you keep all of the chain groups, but instead of looking at the Khovanov differential, well, she introduced a map that turns out to be a differential. Okay, but that's like something you need to prove that looks like this. So there's multiplication, and there's co-multiplication, sort of the same as in Khovanov homology. But what happens is that it's somehow very simple. You send everything to 0, except that x tensor x goes to 1. And remember, in Khovanov homology, it was kind of the opposite. X tensor x would go to 0, and everything else, was non-trivial. And then here, 1 goes to 0, but x goes to 1 tensor 1 again. So it's very different than the Khovanov homology. And what turns out is that because of sort of this term, so this differential, it turns out that it's differential, so d squared is 0. And it also has a by degree 1/4. So in this Khovanov grid, it actually does exactly what the night move looks like. Because remember, night move, I said it's like 1, 2. But remember, in Khovanov homology, we skip every other one. So this is actually 1/4. So what she actually constructed is a map that goes from here to here. Okay? So somehow you want to prove something about this map. Somehow you want to prove that the rank of this map is the same as the number of night move pairs. Right? Because then you will know that they're all paired. Sort of that's the idea. Oh, well, but doing so is not so easy, and actually involves a so-called thing as a double complex. And it turns out that if you consider Khovanov chain complex, Khovanov differential, and this differential defined by her, they do form a bicomplex. So what is a bicomplex? Well, remember, Khovanov differential goes like this. Just shifts things by 1, and it's preserving the second grading, the J grading. So I'll give you a general definition here, although I am running somewhat out of time. But in particular, in our case, DH is going to be D Khovanov, and then what's called the D vertical in this case is going to be D Lee. Okay, and then this is a general construction. So you have a collection of chain groups that live on an integer lattice in R2. And you have the following conditions. So they both have to be differentials. And here I'm sort of specified that they have degree 1, 0, and 0, 1. You can do it with other degrees like we will do here. And then you want them to anti-commute. So what you want is that if you apply one and the other, so if you do this, you go this way, and then you say go up, or you go up, and you go to the right, you get the same result. Okay? Well, with the opposite sign, so that they add up to 0. And it turns out that if this is true, then actually this horizontal differential induces a differential on the homology that's computed with respect to the vertical differential. Because remember, now you have two differentials. So if you compute homology in this direction, you're just going to get Khovanov homology. If you compute homology in this direction, where you're going to get something, it's a differential. I don't know what. But what's really, really kind of crucial here is that somehow if you compute homology, let's say here, then there's a way to upgrade this differential to the map on homology groups that's also going to be differential. So somehow what you do, you start with a plane that's filled in with Khovanov chain groups, Cij of a naught. And then let's say you compute Khovanov differential, and then you get Khovanov Ij of a naught. But then it turns out that this differential will give you some other differential, d Li, induced on Khovanov homology, so that this is again a chain complex. And you can actually iterate this process. So basically, the total complex M with respect to D, with M a graded module over R, and with a homogeneous degree n part equal to the sum of all of these bigradings that end up, such that K and L end up to n, and with respect to the sum of the differentials, well, we can do that because it turns out that the sum of the differentials is also differential, right? Because when we square it, we're going to get dH dV and dV dH, but this is 0 based on the anti-commutativity result. And these are 0 because they're differentials. So basically now you can actually compute the differential with respect to this sum of differentials. And that actually says that there exists a spectral sequence, and again, spectral sequence is basically a collection of these planes, one for each R, where the 0th one is the module that we started with. The first one is homology with respect to horizontal differential, which in our case is going to be Khovanov. And then the second page is the homology of Khovanov homology with the induced vertical differential. Okay, it's a complicated construction, but you know, sort of you can sort of think of it as a very visual one, where you sort of, again, you compute the homology with respect to this one, you replace the whole plane by homology groups, you compute the homology with respect to this one, you replace the whole plane with yet this another homology, and then you just keep changing your groups and your differentials. So basically at each level you have a different collection of groups and a different map. But what happens is that when you start sort of doing this, and again different conventions are different, you're going to have this one, and then you're going to take their sum. And then you're going to take the sum of one of these with two of these, and so on and so on. So sort of taking a steeper and steeper diagonal sort of tells you sort of how to think about this very vaguely and very intuitively. And here's what's going to happen. Well, if M has a bounded support, that means it's maybe on just two diagonals, but also in various homological degrees, then the spectral sequence converges to something. And that's good because sometimes you cannot compute each page. And again, here one of the pages will be Khovanov homology, but maybe you can compute this limit. And that's what we are going to do. Okay, so again, the Khovanov chain complex, Khovanov differential, and the Lie differential form a double complex. So we can just look at this standard construction of a spectral sequence. This rth page means that the dr differential will have a degree 1 for r, so it will not be jumping by 1, it will jump by 4. But remember, Khovanov homology of a thin knot lies only on two diagonals. So the first differential will be of degree 1, 4. The second one will be of degree 1, 8. But that means that it's sending things to 0, because there's nothing on that diagonal. Okay, and that's basically the idea, that this 1, 4 differential will pair everything with these two diagonals, and then the spectral sequence will die on that second page, meaning it's going to become trivial. And that's again for the pure sort of structural reasons that, let's say if you have sort of two things, so this map will pair this one with this one, but if you want to pair with the 1, 8, there's nothing to pair it with, so the map is 0, and the thing stabilizes. Okay, so the theorem is actually that you can compute just the Lie Khovanov homology, and it turns out to be very simple, and I'm almost done. it turns out to be very simple. For an n-oriented n-component link, the dimension of the total dimension of Khovanov-Lie homology is just 2 to the n. Okay, but it turns out again the Lie differential doesn't preserve the grading, so you can think of something that's called Lie filtered homology. And then if you look at the ith degree 1, which considers all of the things up to degree I, that actually depends on the linking number between these components. This is a result for Rento. So it's a very subtle way in which sort of linking numbers contribute between different components, but it may be useful. And then there's again a later result by Rasmussen that there is a spectral sequence whose E2 term is Khovanov homology, and then it converges to the Lie homology. And for a knot, what you're going to get is those 2 copies of Q that pawn move the dimension, because all night moves are paired and killed off. And the only thing that remains is that this little green move of these 2 Z's stacked by one or the other. Shumakovich actually showed that this spectral sequence also works over ZP. And for example, this is, oh, I'm sorry, I have them switched. So this is how it should be the opposite. This is how it looks over Q, and this is how it looks over Z, except that it should be Z2, Z2 here, and Z2, Z2 here. And this is called actually a tetraomino piece. Okay. This is a beautiful note by Barnatan that actually Lou repeated in his paper. In a beautiful article, he introduced a second differential on the Khovanov complex of an outer link and showed that this resulting double complex has a non-interesting homology, just 2 to the n. This is a very interesting result, okay? And it is a very interesting result. So I'm running out of time, so I'll do this tomorrow, but this result was actually used to actually come up with another numerical invariant, but a very sophisticated one, which basically, again, just tells you where these diagonals are, okay? And it's called the Rasmussen S invariant, and sort of literally does that. But then that one can be used to provide a bound on a very, very topological quantity that's called the slice genus. And again, I'll tell you about, I'll stop here and I'll pick up tomorrow. Thank you.